Hi everyone! Today I'll be discussing the benefits of using ATS, which stands for Applied Type System, which is a statically typed functional programming language created by Hongwei Ji. Some of my research interests lie in machine learning, so I decided to implement binary classification as my final project in CS 520, Programming Languages, a graduate class at Boston University. I will talk about the features of ATS that are useful for this task, and then I'll walk through the code with you. First, let's take a moment and think about supervised learning. You might want to ask yourself, what steps does supervised learning always have? Every supervised classifier follows a similar training and testing procedure. We take in a set of training data that is composed of feature label pairs. We feed it into an algorithm or model that learns some information about the data. After, the trained model can then be fed the test data, returning predictions, and then finally, we'll check performance. Regardless of the dimensions of the data, what the data actually represents, or the algorithm you use, the flow for supervised classification remains the same. Now, this is where ATS comes in. One of the underlying motivations in the creation of ATS is to code productively. What does that mean? Well, it can mean a lot of things. But in this context, I'd like to show how writing code with abstraction can be a bit more productive. Let me explain. Often, when writing code, we repeat actions multiple times. Clean the data, train, test, repeat. Usually, when learning how to code, this is where modularity is introduced. The idea that encapsulating actions into functions is not only cleaner and easier to follow, but is more productive, because you don't rewrite the same code over and over again every time you need to perform the same action. You simply call the function performing that action as many times as needed. However, ATS actually takes this form of productivity one step further. It allows for abstract templates, which enable even more productivity than just writing standalone functions. I've created a template for supervised learning, which allows for a high-level view of the flow of a supervised classifier. As I previously mentioned, given an algorithm of choice in a dataset, we train the algorithm, return the trained model, which is usually a set of weights for a linear model, test on the held out data, and repeat. I focused on the simple setting of binary classification and used the well-known iris dataset for the task. I have 3 files I will be discussing. The helper file, which contains helper functions that clean data and aid in the algorithm implementation. Then, I'll walk through the template code that shows the power of ATS in several respects. Lastly, I will explain the actual implementation. Most of the content regarding ATS's use cases and capabilities will be highlighted in the second section, if you're already familiar with some of these machine learning techniques. Here we have a convert string function, which takes in a tuple of real valued features and a string label and converts them all to be numbers. This is necessary for these algorithms, which assume binary labels of 0 and 1, or -1 and 1, for example. Additionally, the iris dataset includes 3 classes, which are different species of the iris flower. But for today, I'll only be dealing with binary classification, so I narrow it down only to the Virginica and Setosa species. This work could be extended to support more complex algorithms such as an SVM, as well as multi-class classification. Moving on, we have a train test split function which takes in all samples and splits them into train and test portions. For the 2 iris classes, there are a total of 100 samples, 50 samples each. Therefore, I take a 90-10 train test split, allowing for 10 samples, 5 of each class, to be classified at test time. Next, some basic functions are needed. We have a sumList function, which takes the sum over every element in a list of float values. We have a function which computes the dot product of 2 lists. We can view each list as a vector and assume they're of the same length. Later, when testing occurs, we will need a way to evaluate how well our model did. Metrics commonly used to evaluate performance include accuracy, precision, recall, and F1 score, which are all defined by equations involving the number of true positives, true negatives, false positives, and false negative labels. The function getBreakdown calculates each of these 4 values based on the predicted and true label input, and then these values can later be used in each metric implementation. Other basic functions include element-wise addition of two vectors, multiplying a vector by a constant coefficient, and taking the L2 norm of a vector. We also have a sign function, which returns the sign of a number, the sigmoid function, which will later be needed in the logistic regression classifier. Subvectors performs element-wise subtraction on two vectors. Convert essentially takes a handcrafted ATS tuple. The @ sign is just declaring a type, and in this case it's a tuple of 4 double values, and reformatting it to be a list of lists to ease the use of features in later functions such as when we take the dot product. If you haven't already noticed, ATS is a typed language, as you can see by my explicit declaration of types of input and output written for each function. While this may seem excessive or time-consuming, it actually becomes incredibly useful later on when we start to implement algorithms in the larger supervised template. These types allow for much easier debugging. Have you ever had extremely strange results when performing some type of supervised or unsupervised learning in Python? Sometimes something is wrong with our input data, we're parsing something to the wrong type, etc. And it can be difficult to locate the issue. Most of the time, interpreted languages won't catch these issues for you. The time spent using types in ATS will save you a great deal of pain and confusion later on. Moving on, we have a matrix dot product, which is essentially performing matrix multiplication with a vector. Vector sigmoid, which calculates sigmoid of every element in a list. Reversed, which reverses a list. And transpose, which transposes a matrix of shape m by n to n by m. As we know, the rows become columns. We have a function that adds 1 to every sample's feature list, which is later used to learn an intercept value for a linear model, also sometimes called the bias coefficient. Lastly, I have written a convert labels function, which is needed for logistic regression, as the sigmoid pushes values to be 0 or 1, and our data labels are initially assigned to -1 and 1. This function converts the labels to match so that training and testing can be correctly performed, as the predicted and true labels are compared in both functions. First, I define some useful data types that will condense the rest of this code. We have a data list which has feature values of type A and label values of type B. I also have representations for train and test lists of just samples and just labels, respectively. Next, I provide function signatures that will later be implemented. What this does is say there will be a function named learn that takes in a data list of types double and double for the features and labels, respectively, an algorithm which takes a train list of samples and labels, and will output the learned model, which in this case will be a list of weights. From this, you can already see the degree of abstraction. We don't need to know what the data is about or which algorithm we will use. These can vary and will be implemented later. Another interesting feature of ATS to note here is that the algorithm being passed in is actually a function itself. This means that the learn function is a higher order function, which means it takes another function as input or output. This is incredibly useful and allows us to further avoid hard-coding function details into the template. Next, there are 2 test function definitions. The first computes a label using the sign of the dot product of a set of weights and the corresponding feature vector, which enables predictions of value -1 and 1. This works for the perceptron algorithm, however it won't for logistic regression. All values in logistic regression are viewed as a probability, and therefore prediction values range between 0 and 1. We will see this more clearly later in the implementation code. The Boolean inter tells us whether we want to fit an intercept value to the linear model or not. Next, we have a scoring function, which is also a second-order function, as it takes in a specific metric function as input. We have function definitions for a handful of performance metrics. The last 2 functions are getData and supervise. GetData separates the feature values from its corresponding label, and supervise is the final template that puts everything together to form our abstract binary classifier. It takes in train and test data, the classifying algorithm, the provided test function, the metrics we want to calculate, and whether the model should fit an intercept. Now looking at the implementation for this template. First, we pass in the training data and the algorithm to learn the template, and expect it to return the model's weights. We then separate the test samples from their labels and pass the samples, weights, and intercept boolean to our test template. which will then give us the predicted labels. Now that we have the predictions, we can compute any list of metrics we want, using the score function and a given metric. Lastly, we will go through the rest of the implementation to see this code in action. The first few lines of codes just import the data from a CSV file. I'm going to skip going over this in detail. We start with the simple implementation of the learn template. All it does is separate data into samples and labels and then feed it into the algorithm function provided, leaving the heavy work for the algorithm implementation itself. Next, we have the two test templates, one which determines a label by taking the sign of the dot product of the learned weights and feature values, and another which thresholds the sigmoid value of the dot product of the learned weights and the feature values. Both have an option for the case that an intercept was learned, and add that to the dot product sum before taking either the sign or sigmoid of that value. We also implement the score template, which is given both the model's predicted labels and the golden or true labels, as well as a metric that is desired to be calculated. It passes the labels to the metric function and then just nicely prints it out. The accuracy, recall, precision, and F1 metrics are clearly computed now, using the false positives, false negatives, true positives, and true negatives of the label breakdown. These metric functions also return a string with the name of the metric, just for display purposes. Moving on to the algorithm implementation, I've written a function called recompute to make some of the perceptron code a little bit cleaner. This essentially performs the weight update rule at a current iteration of the algorithm. Next, the perceptron function. We initialize the weights to 0 and the error to 1 and pass the data into a helper function that essentially is a loop. The loop breaks, or rather the training ends, once all samples in the training data have been correctly classified, meaning the error is 0. If you're more curious about the perceptron algorithm, there are many resources online to view the equations. Lastly, we have functions for logistic regression. The difference between these two functions is whether or not we learn an intercept for the model. You can see that we add another weight to the weights list and add 1 to all sample features in the case that we do learn the intercept. We define the number of steps, which explicitly stops the looping, the learning rate, and the initial weights. We pass this with the data to a helper loop function similarly to the perceptron code. The update rules differ from the perceptron algorithm, but the concept is still the same. Update weights until stopping condition is met. At the very end, we implement our main function to call our supervised template and print out the results. This dataset is linearly separable and performs very well with such simple algorithms. Thanks for watching, and I hope you got to learn a little bit about ATS today.